You are the descendant of the most dangerous animal the Ice Age ever produced. Not the cave lion, not the sabertooth. You. And the proof is hidden in your body right now. In your blood, your skin, and your DNA. These are 10 reasons you survived the Ice Age, and the mammoth did not. All right, let's dive in. Number 10. The shoulder built like a catapult. Raise your arm and pretend to throw something. That ordinary motion you just imagined is one of the most lethal things any animal on Earth can do, and almost nothing else alive can come close. A chimpanzee is roughly twice as strong as you, pound for pound. It can climb faster, grip harder, and tear apart things you could not. But take that same powerful chimpanzee and teach it to throw, and the best it can manage is about 20 miles per hour. A trained human can throw past 90. A 12-year-old in a baseball league can outthrow an adult ape with ease.
Somewhere in our past, the human body became a throwing machine unlike anything in the animal kingdom. In 2013, a team of researchers led by Neil Roach at Harvard worked out exactly how we do it. And the answer is that your shoulder is not really a joint at all. It is a slingshot. When you cock your arm back to throw, you are not just winding up a muscle. You are stretching the tendons and ligaments that cross the shoulder, loading them with elastic energy, exactly the way you stretch a rubber band or draw a bow. Those tissues store that energy for a fraction of a second and then release it all at once, snapping the arm forward and producing the single fastest motion the human body is capable of. Your muscles alone could never move your arm that fast. The elastic recoil of your own shoulder is what flings the projectile. This catapult shoulder did not assemble itself overnight.
The specific anatomy that makes it work, the low and open shoulders, the mobile waist that lets your torso twist and store even more energy, the precise twist in the upper arm bone, all of it first appears together in the fossil record around 2 million years ago, in our ancestor Homo erectus. And it appears at exactly the moment our ancestors were becoming serious hunters. That timing is almost certainly not a coincidence. The anatomy behind all this is a quiet revolution that took millions of years to assemble. Compared with a chimpanzee, your shoulders sit lower and face outward rather than up toward your ears, which lets your arm swing far back and rotate through a huge arc. The upper arm bone itself carries a subtle twist that a chimp's does not. Your waist is tall and flexible, so your hips and torso can rotate almost independently, winding the body like a spring before it unwinds into the throw. Darwin himself noticed, more than a century ago, that walking upright had freed our hands for exactly this kind of work, though he had no idea of the machinery involved. And there is a price written into our bodies for this gift. The same elastic tissues that store throwing energy are the ones that tear and wear out in baseball pitchers. A modern reminder of just how much force passes through that joint. Think about what this gave a small, fangless, clawless primate standing on an open plain. Every other predator of the Ice Age had to close the distance, to come within range of hooves, horns, and tusks, and risk being killed in the act of killing. The human animal could stand back and reach across that gap. A thrown stone, and later a thrown spear, let you strike a creature that could crush you from a distance where it could not strike back. You did not have to be stronger than a mammoth. You had to be able to hurt it from 10 meters away, again and again, without ever stepping into the kill zone of its tusks. The catapult in your shoulder was the first thing that made that possible. Consider what a difference distance makes to a soft, breakable animal like us. A lion or a wolf has to close with its prey and absorb whatever the prey does in return. The kick, the gore, the trampling. A thrown weapon severs that bargain. It lets a fragile hunter inflict a mortal wound from outside the reach of hoof and tusk and horn, then simply wait. And the archaeological record shows our ancestors pushing this advantage further and further. Stone-tipped projectiles appear hundreds of thousands of years ago, sharpening the wound a thrown shaft could deliver. No other primate hunts this way at all. We are the only lineage that turned the empty air between predator and prey into a killing field, and it began with the strange catapult buried in the shoulder. And the archaeology backs this up. Among the oldest weapons ever found are a set of wooden throwing spears from Schöningen in Germany, around 300,000 years old, balanced and weighted like a modern javelin. Clear evidence that our ancestors were hurling projectiles at large animals deep in prehistory. Later, humans amplified the catapult even further with the spear thrower, a simple lever that extends the arm and sends a dart flying with even more force. But the raw equipment was always the body itself, that low-slung, spring-loaded shoulder, paired with an accuracy no other animal can match. It was not enough to throw hard. You had to throw hard and hit a moving target the size of a heart. And the human nervous system, wired to that catapult shoulder, could do both. The control behind the throw is as remarkable as the power. To put a spear through a moving target the size of a dinner plate, the brain must time the release to within a few thousandths of a second, coordinating dozens of muscles in a precise cascade. Few motor tasks the human body performs are more demanding, and we do it almost without thinking. This is the deep reason a sport built entirely around throwing a small ball can hold the attention of millions. We are watching, refined to its peak, the single most distinctively human physical act there is. And this is what makes the throw so central to the human story. We are not natural-born killers in the way a big cat is, armed at birth with claws and a killing bite. We are a soft, slow primate that engineered lethality from the outside in, and the thrown projectile was the first and most important step. It let a creature with no natural weapons become, in effect, the only primate ever to hold the role of an apex predator, striking down the largest animals in its world from a safe distance.
The catapult shoulder did not just feed us. It rewrote what kind of animal we were. But a weapon is useless if you cannot run your prey down. And that gift is hidden not in your bones, but across the whole surface of your skin. Number 9. 4 million tiny weapons in your skin. Here's something no other large animal can do. On a blazing hot afternoon, you can move steadily for hours, while almost every animal you might want to hunt is forced to stop and rest in the shade. The reason is written across the entire surface of your body, and you are using it right now without noticing. You have somewhere between 2 and 4 million sweat glands packed into your skin. No other large mammal comes anywhere close to that number, and combined with the fact that we lost almost all of our fur, it turns the human body into the most efficient cooling system in the animal kingdom. The physics of this is brutal and beautiful. When you exert yourself, your muscles generate enormous amounts of heat, and an overheating body shuts down fast. Most large mammals dump that heat by panting, breathing rapidly to evaporate moisture from the mouth and lungs. But here's the catch. An animal galloping at full speed cannot pant effectively because its breathing is locked to the rhythm of its stride. So a running antelope or horse builds up heat faster than it can shed it. It can sprint away from you in seconds, but it cannot keep that up. It has to stop and pant and cool down. You, drenched in sweat that evaporates straight off your bare skin, do not. You can keep moving while your prey is forced to halt. This is the foundation of the endurance running hypothesis, championed by researchers like Daniel Lieberman, which argues that the genus Homo evolved, around 2 million years ago, into a creature built for long-distance pursuit in the heat. Long legs, springy tendons, a stable head, and above all that vast sweating capacity, all point to a body shaped for going far rather than fast. The dramatic version of this is persistence hunting. The idea that early humans simply followed an animal at a steady jog through the hottest part of the day, never letting it rest, until it collapsed from heat exhaustion and could be walked up to and killed, without a single weapon. There are actually 2 kinds of sweat, and the difference is part of what makes us special. Most mammals that sweat at all rely mainly on apocrine glands, tied to hair follicles, which produce a thicker secretion. Humans are dominated instead by eccrine glands, which pump a thin, watery sweat straight onto bare skin, where it evaporates almost instantly and pulls heat away with astonishing efficiency. Pair that with the loss of nearly all our body hair, and you have a cooling system that works like a radiator running flat out. There is a reason marathons are run by humans and not by horses. Over a long enough distance, in the heat, a fit person can outlast almost any four-legged animal on the planet, including the fastest ones. Speed belongs to the antelope. Endurance belongs to us. Here the ground gets shakier, because persistence hunting is genuinely debated. Documented cases of modern hunter-gatherers actually doing it are rare, and some researchers argue it was never a common strategy. Others pushed back hard. A 2024 study gathered nearly 400 historical and ethnographic accounts of endurance pursuits from around the world, and argued the method was far more widespread and efficient than the skeptics claimed. The argument is still live, but the underlying machinery is not in doubt. Your ability to shed heat and keep moving while your prey overheats is real. It is exceptional, and it is yours.
A small Welsh town runs a vivid modern test of all this every year. A race that pits human runners against horses and riders over a punishing cross-country course. And on hot years, often enough to matter, a human being crosses the line first. A horse is faster over any short distance you care to name. But stretch the contest out, add heat, and the advantage quietly slides toward the sweating, upright, bare-skinned animal that can keep going when the horse must stop. Our ancestors did not need to be quicker than their prey. They needed the prey to overheat first. And in the long game of heat, almost nothing on four legs can beat us. That 2024 reanalysis is worth a closer look, because it gathered nearly 400 recorded endurance pursuits from foraging peoples across the globe, and calculated that, in the right conditions, the return on a long chase could rival or beat other hunting methods of the time.
Among the sand of the Kalahari, hunters have been documented running antelope down across the open sand under the midday sun, following the tracks for hours until the animal, unable to cool itself, simply stops. There is even a hidden limit on the human side of this contest, because the brain itself can only tolerate so much heat, and our cooling system is, in part, what keeps the most precious organ from cooking during the chase. This gift came with a bill, and it is one we still pay. All that evaporating sweat is water, and water leaving the body must be replaced or the system fails. The same adaptation that let our ancestors outlast their prey also made them uniquely thirsty animals, dependent on finding and carrying water in a way few other creatures are. It is very likely that the need to haul water across the hot, open country drove some of our earliest containers and planning. To hunt by endurance, you first had to solve the problem of carrying your own ocean with you.
The midday timing carried a hidden bonus, too. The blistering middle of the day, when the heat tilts the contest in favor of a sweating human, is exactly when the great cats and other ambush predators are forced into the shade to cool down. By making the noon sun their ally, our ancestors could hunt in the one window when the competition and the danger had largely shut down for the day. The same heat that broke their prey also cleared the field of rivals, leaving the sweating, upright, water-carrying hunter almost alone on the burning plain. Other animals had claws and fangs. We had sweat. And in the long, hot pursuit, sweat is the deadlier weapon. Number 8. Eyes designed to be read. Look at another person's eyes, and you can tell, instantly and precisely, exactly where they are looking. You do this thousands of times a day without thinking about it. It feels completely ordinary. It is, among animals, almost bizarre.
Because nearly every other primate on the planet has the opposite arrangement. Dark, heavily pigmented eyes, where the colored part and the surrounding area blend together, making it very hard for an outside observer to tell which way the animal is actually looking. Human eyes broke that rule. We have a bright, high-contrast eye, with a visible pale region surrounding a dark iris. An eye that broadcasts the direction of our gaze for anyone to see. The classic explanation for this is called the cooperative eye hypothesis, and it is genuinely elegant. For most animals, hiding the direction of your gaze is an advantage. A predator does not want to telegraph which prey it has locked onto. A prey animal does not want to reveal that it has spotted the lion. Concealing your gaze is the safe default. So the fact that humans evolved in the opposite direction, toward eyes that openly advertise where we are looking, suggests we became a species for whom the benefit of silent, eye-based communication with our own kind outweighed the cost of giving our attention away. There is a famous experiment where a researcher looks up at the ceiling, and apes tend to follow the movement of his head, while human infants follow his eyes alone. We are tuned, from infancy, to read each other's eyes. Picture what that does for a group of hunters surrounding a dangerous animal. No words, no gestures, no sound that might spook the prey or give away your position. Just a flick of the eyes from one person to another. There, now, you. A whole coordinated assault, planned and triggered in silence through nothing but the visible whites of the eye. It is a tool for wordless teamwork against something far bigger than any one of you. There is a deeper experiment behind this idea, and it is worth picturing. A researcher sits in front of a chimpanzee and then in front of a human infant and slowly looks up at the ceiling using only the eyes, with the head held still. The chimpanzee, overwhelmingly, fails to follow a gaze signaled by the eyes alone. It tracks the head. The human baby, far too young to speak, follows the eyes almost every time. We are born primed to read the eyes of others and to have ours read in return. Some researchers tie this to a broader idea sometimes called self-domestication, the notion that our species was selected over many generations for tolerance and cooperation, for being able to live and work in close groups without constant conflict, and that our open, readable faces and eyes are part of that gentler, more cooperative package. But this beautiful story has taken some real hits lately. For years, it was claimed that fully white, visible sclera was unique to humans. More recent work has shown that is not quite true.
A 2023 study found that chimpanzees and several other mammals show visible white in their eyes more often than anyone had reported. And a broad 2025 review challenged nearly every pillar of the cooperative eye hypothesis, arguing the evidence that our eyes are uniquely built for cooperation is weaker than the textbooks suggest. That simple glance may carry even more than coordination. Meeting another person's eyes is one of the deepest social signals we have. It builds trust, soothes infants, and underlies the way we teach, with a learner watching exactly where a skilled elder is looking to know where to attend. A child can learn to nap a stone tool, or read a track in part by following the gaze of someone who already knows how. No words required. An animal that hides its eyes cannot teach or learn this way. An animal whose eyes openly broadcast attention can pass a skill from one generation to the next through a look. Whatever first produced our bright, readable eyes, they became a channel not just for hunting in silence, but for handing down everything we knew. So the picture is murkier than the clean story. There is even a quieter explanation on the table, that the pale, uniform look of the human eye is partly an accident of pigmentation drift rather than a finely honed signal, and that we simply learned to make brilliant use of whatever eyes we ended up with. What remains true is that humans really do have unusually visible, high contrast, easy to read eyes, and we are exquisitely good at reading each other's gaze. So good that a hunter can tell across a clearing the exact instant a companion locks onto the target. Whether it was sculpted for cooperation or merely seized upon, that ability still let your ancestors hunt as a single, silent organism with 20 pairs of eyes. Those visible eyes leak more than direction. They leak emotion and health. The whites of a tired or sick person redden and dull. Fear widens the eye and exposes more white. A steady gaze can calm a frightened infant or steady a nervous companion. An animal that wears its attention, its mood, and its condition openly on its face is an animal built for a life of intense, constant, close cooperation, where reading one another correctly is a matter of survival. We did not just evolve eyes that could be followed, we evolved eyes that could be trusted. You would not survive the Ice Age without the next adaptation either, and it sits in the middle of your face. Number 7. A nose built for killing cold. Step outside into genuinely cold air, the kind that bites at 40 below, and take a deep breath through your mouth. It hurts. Now breathe through your nose instead, and it is bearable. That difference is not trivial. It is the difference between hunting in a frozen world and dying in it. And the people who pushed into the brutal cold of Ice Age Europe and Northern Asia carried in the middle of their faces an adaptation tuned for exactly this problem. The job of the nose is not just to smell, it is an air conditioning unit. As you inhale, air swirls through the twisting passages and sinuses inside your nose, and in that brief journey it is warmed toward body temperature and loaded with moisture before it ever reaches your lungs. This matters enormously in the cold, because frigid, bone-dry air hitting delicate lung tissue is genuinely dangerous, and it strips heat and water out of your body with every breath. And here is the striking part. The shape of the human nose tracks the climate our ancestors lived in.
Populations whose forebears endured cold, dry environments tend to have taller, narrower nasal passages, geometry that forces the air into longer contact with warm, wet tissue, conditioning it more thoroughly before it goes deep. The nose, quite literally, is shaped by the cold. The link between the shape of a nose and the climate it evolved in is now well documented. Researchers have found that nasal dimensions across human populations track ancestral temperature and humidity in a consistent way. People whose ancestors lived in cold, dry air tend toward narrower, higher nasal openings, while those from hot, humid regions tend toward wider ones. The pattern is strong enough that it is treated as a real signature of natural selection acting on the face, fine-tuning the body's air conditioner to the air it would have to breathe.
Inside that nose, the turbinates, delicate scrolls of bone draped in warm, wet tissue, create a huge surface area that the incoming air must wash over, so that by the time a breath reaches the lungs, it has been pulled most of the way to body temperature, even on a brutal day. This is also one of the features that stands out in the Neanderthals, our cold-adapted cousins, who had famously large noses and big, sinus-bearing faces. For a long time, the assumption was simple. Big nose, cold climate, obviously a heater for freezing air. The reality, as researchers have dug in, is more debated. Some studies using airflow modeling suggest the large Neanderthal nose was as much about moving huge volumes of air to fuel a hard-working, high-energy body as it was about warming it. Inside the nose, the engineering is extraordinary. Curled within each nasal passage are the turbinates, thin scrolls of bone wrapped in moist, blood-rich tissue, and they pack an enormous surface area into a tiny space, forcing every incoming breath to wash across warm, wet membranes. Breathe through your mouth in deep cold, and you bypass all of it, dumping frigid, dry air straight toward your lungs and losing precious heat and water with every exhalation. Breathe through that finely tuned nose, and the same air arrives warmed and humidified, the body's water and warmth conserved. Over a long day of hunting in lethal cold, that difference, repeated with every single breath, is the quiet line between an animal that can work in the freezer and one that cannot. So the precise story of why their faces looked the way they did is still argued over. There is even a related cold adaptation in the flatter, fat-padded faces of some Arctic peoples, geometry that reduces the exposed surface where frostbite bites hardest. But strip away the debate, and the core fact stands. To hunt a woolly rhinoceros across a frozen steppe, every breath has to be warmed and moistened before it reaches your lungs. And the human face, refined over countless generations in the cold, does exactly that. breath after breath, in air that would otherwise sear the lungs raw. The nose does still more than warm the air. It traps dust, smoke, and airborne particles before they reach the lungs, and the moisture it adds keeps the delicate inner tissues from drying and cracking in the desiccating cold. Lose that conditioning by breathing hard through the mouth in a freezing wind, and the lungs take the full assault of raw, frozen, dirty air. For people whose lives depended on long days of exertion in some of the harshest air on Earth, that humble organ in the center of the face was doing quiet, ceaseless, life-preserving work with every breath drawn on the hunt. The pattern holds right to the present day.
The narrowest, highest nasal passages in the world are found in the peoples whose ancestors endured the coldest, driest conditions, in Siberia and the high north, while the broadest are found near the warm, humid equator. The human face, in other words, still carries a readable map of the climates our ancestors survived, written in the geometry of the nose. Nowhere else does the outside world reach so plainly into the body and reshape it to fit. You cannot chase a mammoth across the tundra if breathing the air is killing you. Your face made sure it was not. Number 6. The famine gene that now haunts you. Ice Age life was a violent feast or famine cycle. A successful hunt meant a sudden, enormous windfall of meat and fat, far more than you could eat at once, followed sometimes by weeks of nothing while the group searched for the next kill.
A body that could gorge on that windfall, bank the energy efficiently, and then run on those reserves through the lean stretch had a powerful survival edge. And there is an ancient version of a gene carried in our species that appears to do exactly that kind of work, tied to how we handle fats and energy. It is called ApoE, and the oldest version of it, the one our ancestors started with, is the variant known as E4. ApoE4 is the original. It is the ancestral form, the one the genus Homo carried for most of our history, and it plays a central role in how the body transports and processes fats and cholesterol. The leading idea, sometimes called the thrifty gene hypothesis, is that in a world of scarcity and hard physical effort and constant exposure to infection, this version offered real advantages: efficient handling of fat and a more aggressive immune response against the parasites and pathogens that surrounded our ancestors. In an Ice Age body, lurching between glut and starvation, a gene that helped you make the most of a fatty meal and fight off infection was a gift. To understand why this gene stuck around, you have to understand the world it was built for. Our ancestors lived under relentless pressure from infection, parasites, and injury, with no medicine and no guaranteed next meal. A version of ApoE that mounted an aggressive inflammatory defense against pathogens and that squeezed maximum value out of every scarce fatty meal was exactly what a body needed when the threats were infections and starvation, and the average life was short and hard. ApoE4 is, in that sense, a young person's gene, tuned to get you through the dangerous early decades of a brutal life, when surviving the next infection or the next lean winter was all that mattered, and the distant problems of old age were a luxury almost nobody lived long enough to face. And now here is the twist. The reason this gene is famous today, and it is not a happy one, that same ancestral variant, ApoE4, is the single strongest common genetic risk factor for late-onset Alzheimer's disease. Carrying it substantially raises your odds of developing dementia in old age, and around a quarter of all people carry at least one copy. The very gene that may have helped your ancestors survive the cold and the hunger of the Ice Age appears to turn against you in a modern world of abundant food, long lifespans, and constant calories. An adaptation perfectly tuned for a harsh, short, active life has become a liability in a soft, long, sedentary one. And the survival benefits of ApoE4 remain a hypothesis, an inference about the past rather than a closed case, with scientists still untangling exactly what this gene did and why it persisted. The gene's history adds another layer to the irony. ApoE4 is the original version, But our species later evolved two newer variants, the ones now most common in much of the world, which appear to carry less of that late-life risk. In other words, evolution itself seems to have been quietly walking back the ancestral gene as human life changed. Yet ApoE4 never disappeared. Roughly a quarter of people still carry a copy, and the small fraction who carry two face a steeply higher risk of Alzheimer's. We are, many of us, still running ancient Ice Age software on a body now expected to last 80 or 90 years, decades longer than the world that wrote the code ever asked of it. A final strange wrinkle goes by the name of the ApoE4 paradox.
In some populations near the equator, where this ancestral gene is still common, the expected epidemic of dementia does not appear in the way it does in the industrialized world, which hints that ApoE4 only turns toxic in a very particular modern setting, one of rich food, long life, and little physical hardship, the exact opposite of the world it evolved for. The gene did not change. We did, by building a world it was never designed to inhabit. Part of what keeps this gene around may be that its costs arrive late and its benefits arrive early. Whatever ApoE4 does to raise dementia risk, it does so mostly in old age, long after most of a person's children are already born and raised. Natural selection is nearly blind to what happens to a body after it has reproduced. So a gene that strengthened a young hunter and only turned dangerous decades later would pass down the generations almost untouched by selection's pruning. The disease that now frightens us was, to the cold logic of evolution, simply too far in the future to matter. This particular gene, of all genes, became a double-edged sword for a reason. ApoE does its work ferrying fats and cholesterol, and the brain is the fattiest, most cholesterol-hungry organ in the body, built and maintained out of exactly the materials ApoE moves. A version tuned to shuttle those materials aggressively could have helped build and fuel a young, growing brain in a harsh world, even as the very same aggressive handling continued across many extra decades of modern life, helped lay the groundwork for the disease that erodes the brain in the end. The gene that may have helped build the mind can also, given enough time, help dismantle it. The shape of the story stops you cold. A piece of Ice Age survival gear, still loaded in your DNA, still firing, in a world it was never built for. Your ancestors may have lived because of this gene.
Some of us will lose our minds to it. Number 5. The shortest sleep of any ape. You are, by the standards of your own family, an insomniac. Among the great apes, humans sleep the least. We average around 7 hours a night. Our closest relatives sleep substantially more. Estimates for chimpanzees, gorillas, and orangutans run well beyond ours, in some cases stretching toward 11, 12, even more hours of sleep a day. Much of it in elaborate nests built fresh each night high in the trees. We sleep less than any of them, and yet we are not obviously worse off for it. The answer to that puzzle is one more quiet Ice Age adaptation. Human sleep is not just shorter, it is denser. We pack a remarkably high proportion of deep, restorative sleep, including the dream-heavy stage known as REM, into our brief nights, getting more recovery per hour than our long-sleeping cousins do.
It is as if evolution compressed the necessary work of sleep into the smallest possible window. And the reason that window had to shrink is grimly obvious once you picture where our ancestors slept. The apes sleep safely, high in trees, on platforms they weave each evening, out of reach of most predators. Our ancestors came down to the ground. And the ground, in a world prowled by cave lions, hyenas, and sabertooths, is the most dangerous place imaginable to lose consciousness for half a day. Before we get to the clever part, it is worth dwelling on just how lethal sleep is in the wild. Sleep is the one thing every animal must do, and the one thing that leaves it completely defenseless, blind and deaf and slow to react, for hours at a stretch. For a tree-sleeping ape, tucked high on a woven platform, That is a manageable risk. For an ancestor who had committed to life on the ground, surrounded by the most fearsome predators the Ice Age could produce, it was the single most dangerous thing the body was forced to do every single night. Evolution could not simply abolish sleep. The brain depends on it far too deeply. So it did the next best thing. It made our sleep as short, as efficient, and as collectively guarded as it possibly could. So we did two things. We made sleep shorter and more efficient, and, just as importantly, we staggered it. There is an idea called the sentinel hypothesis, supported by studies of modern hunter-gatherer groups, which found that within a group, people drift off and wake at slightly different times. The older members tending to sleep earlier and wake earlier, the younger ones the reverse. Across a whole camp, the result is that at almost no point in the night is every single person asleep at once.
There is nearly always someone awake, someone tending the fire, someone who would notice the shape moving at the edge of the dark. The group itself became a creature that never fully sleeps, sleeping long and deep all night, alone, the way every other ape does, would have been a death sentence on the open ground. We survived by sleeping light, sleeping short, and never all closing our eyes at the same time. And the short night bought us something beyond mere safety. Other apes, settling into long sleep at dusk, simply switch off. Our ancestors, awake longer around a fire, gained hours that no other primate had, the firelit evening. Studies of modern foragers find that the talk around the night fire is different from daytime talk, less about chores and conflicts, and more about stories, myths, distant people, the imagined and the absent, the very stuff of culture. By trimming our sleep and gathering in the dark around a flame, we may have opened the nightly window in which human imagination, memory, and shared identity were actually built. The same pressure that kept us alive against the predators also handed us the evenings in which we became storytellers. The Hadza of Tanzania gave researchers a striking glimpse of this in action. Over a study spanning many days and thousands of hours of recorded rest, scientists found that across a group of roughly 20 adults, there were only a tiny handful of minutes in total when every single person was asleep at the same moment. The rest of the time, always, someone was awake. No assigned shifts, no guards posted, just the natural drift of different bodies on different clocks, adding up to a camp that kept one eye open all night long without anyone trying. Dreaming itself may be part of the bargain. The dense REM sleep we cram into our short nights is the stage most tied to processing emotion and weaving the day's experiences into lasting memory. Exactly the kind of mental housekeeping a creature that survives by learning and remembering would need most. We did not simply sleep less. We made the little sleep we kept work harder, consolidating the skills and the hard lessons that a long, dangerous, knowledge-dependent life demanded. Then woke, sooner than any other ape, back into a world we had to stay sharp to survive. From here, the reasons you survived stop being traits every human shares and become gifts handed to specific peoples by a ghost lineage of humanity, starting at the roof of the world. Number 4. A gift from a ghost. Written for the mountains. Take most people from sea level and drop them on the Tibetan Plateau, more than 4,000 meters up, and their bodies panic. The air holds far less oxygen, and the standard human response is to flood the bloodstream with extra red blood cells to compensate. In the short term, that helps. In the long term, it is dangerous, thickening the blood, straining the heart, and causing serious complications, especially in pregnancy. And yet, Tibetans live their entire lives up there, generation after generation, working and thriving at altitudes that leave lowlanders gasping. And they do it without that dangerous overproduction of red blood cells. They carry a genetic adaptation that lets them use thin air efficiently. And the origin of that adaptation is genuinely astonishing. The gene at the center of this is called EPAS1, and it regulates how the body responds to low oxygen. In 2014, a landmark study found that the special Tibetan version of EPAS1 did not evolve from scratch in their ancestors. It was inherited through interbreeding from the Denisovans, a mysterious, now extinct species of archaic human known mostly from a few bones in a Siberian cave. Tens of thousands of years ago, the ancestors of modern Tibetans met and mixed with these archaic people, and one of the fragments of DNA that crossed over was this altitude gene. The Denisovans, it seems, may already have been adapted to high, cold places, and they handed that adaptation across the species barrier to us. The discovery rests on one of the strangest twists in recent science. The Denisovans were essentially unknown until 2010, when DNA extracted from a single finger bone in a Siberian cave revealed an entire branch of humanity nobody had suspected. We still have only a handful of their physical remains, and yet their genetic legacy is woven through living people across Asia and beyond.
The Tibetan version of EPAS1 is a near-perfect match to the Denisovan sequence, and it appears almost nowhere else on Earth. Found at high frequency only in Tibetans and their neighbors, and in those long-dead archaic bones. It is as close as genetics comes to a signed gift, handed across more than 40,000 years from one kind of human to another. Sit with how strange that is. A whole population of humans is able to live on the highest plateau on Earth because of a gift from a different, long-extinct kind of human. A ghost lineage that lives on only in scattered bones and in the DNA it left inside us. This is not some abstract footprint either. That borrowed gene is the difference between flourishing in the high country and slowly failing there. It opened an entire world, the great cold highlands and the animals that lived in them, to people who could now breathe up there. The way the Tibetan body uses that gene is its own quiet miracle.
Rather than thickening the blood with extra red cells, the adaptation keeps red cell counts near normal and instead improves how efficiently oxygen is delivered and used, with better blood flow through the tiniest vessels. The result is a population that can be pregnant, work hard, and raise children at altitudes where unadapted bodies struggle to do any of those things safely. And this matters for the deep story of survival, because the high cold plateaus were not empty. They held their own herds, wild yak, antelope, wild sheep, and the people who could breathe up there could follow and hunt them, claiming a whole vertical world of the planet that was sealed off to everyone else. The clincher came from the ground itself. In 2019, scientists identified a jawbone from a cave on the edge of the Tibetan plateau as Denisovan, and a very old one, showing that these archaic people were living at high altitude on the plateau long before modern humans arrived. The creatures who first solved the puzzle of breathing thin air may genuinely have been the Denisovans, and they were already up there, in the cold and the low oxygen, perfecting the very adaptation they would one day pass into us. The gift was not abstract. It came from people who had lived on the roof of the world first. It helps to know what the gene actually spares people from. At high altitude, the unadapted body's flood of extra red blood cells can tip into deadly conditions in which fluid leaks into the lungs or the brain swells, killers that stalk climbers who ascend too fast. The Denisovan version of the gene sidesteps that whole dangerous response, letting Tibetans live their entire lives where a lowlander could sicken in days. People have been on that plateau for tens of thousands of years, hunting its wild yak and antelope across some of the highest ground any humans have ever called home. And they could only do it because of a borrowed stretch of ancient DNA. And the proof that this was a real, hard-won edge is what happened to people who lacked it. High in the Andes, a completely separate population adapted to thin air as well, but by a different genetic route entirely. Their bodies forced to find their own answer because no ghost ever handed them one. Two peoples, two solutions, one merciless problem, and only the Tibetans were given a shortcut. From the roof of the world, that same kind of inheritance surfaces again at the opposite frozen extreme of the Earth. Number 3. The Arctic inheritance. Now go from the highest place on Earth to one of the coldest and harshest, the Arctic, and consider the Inuit, peoples who built thriving lives in a frozen world on a diet that would wreck most human bodies, a diet enormously high in fat, drawn from seals, whales, and other marine animals.
Living in deep cold and eating that much fat both place specific demands on the body. Demands around how you store fat, how you distribute it, and how you generate heat. And once again, the people who met those demands carry, in their genes, the fingerprints of an adaptation tuned precisely for it. The genetic signal here centers on a region containing a gene called TBX15, which is involved in how the body lays out its fat and in the development of the kind of fat that produces heat rather than just storing energy. In the populations of the Arctic, this region shows strong signs of having been shaped by natural selection for life in extreme cold. And in 2017, researchers found something familiar. This beneficial Arctic variant, too, appears to have come into the modern human gene pool from an archaic source, most likely from the Denisovans or a Denisovan-related population, the same kind of ancient inheritance that gave Tibetans their mountain lungs.
The biology underneath this is its own marvel. Not all body fat is the same. Some of it simply stores energy, but another kind, sometimes called brown or beige fat, exists mainly to burn energy and generate heat, a built-in furnace that helps keep a body warm in the cold. The gene region highlighted in Arctic peoples is involved in how the body lays out its fat and develops these tissues, exactly the kind of machinery you would want turned up if your ancestors faced endless winters and lived on the fat of seals and whales. It is a beautiful match of inheritance to environment, a genetic setting for fat and heat, carried by the very people who needed it most, in the coldest inhabited places on the planet. So, a second time, at the far frozen edge of the inhabitable world, a population of modern humans was handed a crucial piece of survival equipment by an archaic species we barely knew existed 20 years ago. Living Inuit carry in their cells an adaptation to Arctic cold that traces back to an extinct kind of human who walked the cold of Asia long before them. I should note that the Denisovan origin of this particular variant is a strong inference rather than an ironclad certainty. The science here is newer and still firming up. But the pattern it reveals upended how recently we thought our biology was written. And the Arctic diet demanded more than one fix. Alongside the fat and heat gene, Inuit populations also carry tuned versions of genes that handle the processing of the omega-rich fats of fish and sea mammals, an entire genetic package assembled for a life lived on blubber in the cold. It is a body rebuilt, gene by gene, for a world of ice and fat that would sicken almost anyone else. The Arctic body was reshaped in more ways than one. Beyond the gene for fat and heat, peoples of the far north tend toward compact, heat-conserving body proportions, and many carry a particular metabolic variant that changes how they handle the relentless fat of their diet, letting them run on seal and whale blubber without the problems such a diet would cause in others. It is not a single switch, but a whole suite of adjustments, anatomical and metabolic and genetic, layered together into a body that treats brutal cold and a diet of pure fat as normal, even comfortable. Few human populations show so clearly how completely our species can be retuned from the inside out to a place that should be unlivable. The cold itself reshaped the body's outline. Peoples long settled in the far north tend toward shorter limbs and stockier, more compact frames, a geometry that conserves heat by reducing the surface area through which it escapes. The same principle that makes an Arctic fox rounder and shorter-eared than a desert one.
Layer that body shape over the metabolic and genetic tuning already in place, and you have a human form sculpted at every level, from the silhouette down to the chemistry of its fat, for a world of ice. Few human populations have ever been remodeled this completely. The diet drove its own adaptations, too. A life lived on the fat and protein of sea mammals, with almost no plants, would push most people into a strained metabolic state. Yet Arctic peoples carry genetic tuning that lets them run on it smoothly, generation after generation. Every part of the equation, the cold outside and the fat within, was met by a body quietly rewritten to handle it. It is one thing to visit such a world wrapped in technology. It is another to be built, in your very cells, to belong there. A living people, thriving at the frozen edge of the earth, on survival equipment quietly handed down from a human species that died out before history began. Number 2. The organ that eats you alive. There is an organ in your body that makes up only about 2% of your weight, and yet it devours roughly 20% of all the energy you burn, even when you are sitting completely still. 1/5 of everything you eat goes to feeding it. By the cold arithmetic of survival, that is an outrageous, almost reckless expense. Any animal carrying a fuel-guzzling organ like that had better be getting something extraordinary in return. We were. That organ is your brain, and the return on it was the ability to do something no other animal on Earth could. Plan the death of a creature 100 times your size. A single human is a poor excuse for a predator. We are slow, weak, soft-skinned, and unarmed by nature. One human against a 9-ton mammoth is simply a meal waiting to happen. But 20 humans with big, expensive, scheming brains are something else entirely. They can study a herd for days and learn its habits.
They can read the landscape and see, in a cliff edge or a bog or a narrow ravine, a trap that nature built and the mammoth cannot perceive. They can assign roles, set an ambush, drive the giant toward the killing ground, and coordinate the strike. The mammoth has tusks and bulk and raw power. The humans have a shared plan, and the plan wins. There is a long-running idea about how we could ever afford such an organ, called the expensive tissue hypothesis. Brain tissue is metabolically ruinous, and you cannot simply will more energy into existence. So as the human brain ballooned, something else had to give, and the leading candidate is the gut. Our digestive system shrank relative to our body size, which works only if you are eating richer, easier food. Meat from hunting, and crucially the invention of cooking, which pre-digests food with fire and unlocks far more energy from every bite, may have been what paid the brain's enormous bill.
Over roughly 2 million years, the human brain tripled in size. A runaway investment that only made sense because of what it returned. Cooperation, foresight, memory, and the ability to outthink animals that could have crushed us without effort. This is the thing the metabolic cost bought. A wolf pack hunts with instinct and teamwork, and they are magnificent at it. But they cannot invent a new strategy for a new landscape on the spot, teach it to each other, and refine it the next week. A group of large-brained humans can. The brain let our ancestors turn the whole world into a weapon, to use terrain, fire, timing, and cooperation to bring down animals that should have been completely beyond the reach of a fangless ape. It is the most costly organ in the animal kingdom, and the Ice Age megafauna are the reason it was worth every calorie. The brain did not come cheap in any sense. Paying for it meant trade-offs written deep into our biology. A shrunken gut that demanded richer food, and a skull so large that human birth became uniquely difficult and dangerous. A baby's big head forced through a narrow, upright pelvis. We pay, even now, for the size of our own minds. There is also a strong case that the brain grew not only to hunt, but to handle each other. Keeping track of dozens of relationships, alliances, debts, and grudges within a group is its own enormous computational task. And the social demands of group living may have driven brain size as much as the demands of the hunt. Whether aimed at the mammoth or at the politics of the campfire, the result was the same. An organ powerful enough to model the world, and the people in it, several moves ahead. We can still see the results in the ground. sites where whole herds were driven to their deaths in a single planned ambush, and, in the cold of Eastern Europe, huts built from the stacked bones of dozens of mammoths. The architecture of people who had turned their largest enemy into a building material. One invention above all may have made the expensive brain affordable: fire, and the cooking it allowed. Cooked food is, in effect, partly digested before it is ever eaten, releasing far more energy with far less effort than raw food. And many researchers argue this is what unlocked the calories a ballooning brain required. We are the only animal that cannot thrive on raw food alone in the wild. We are obligate cooks. Our very guts and teeth shrunk on the assumption that fire would do part of the work of digestion. The brain that planned the mammoth's death was, in a real sense, paid for at the campfire. The brain may have grown as much to manage each other as to manage prey.
Across primates, the size of the thinking part of the brain tracks the size of the social group an animal lives in, and humans sit at the very top of that scale, wired to track an enormous web of relationships. Who owes whom? Who can be trusted? Who wronged you last season? Coordinating a mammoth hunt and navigating the tangled politics of a band of 100-odd people are, to the brain, versions of the same staggering computational problem, and our ancestors were solving both at once. But a brain full of brilliant plans is useless if you cannot get the plan out of your skull and into the minds of the people beside you. And that brings us to number 1, the reason behind all the others, and the one almost everyone gets wrong. Number 1. The story we tell about how we learn to speak. Everything on this list so far amounts to nothing without one final ability: the power to share what is inside your mind. A plan to trap a mammoth is worthless if you cannot explain it. Knowledge of where the herds migrate, of which valley floods in spring, of how a hunter died last winter so that you do not die the same way. All of it is useless if it cannot pass from one mind to another and from one generation to the next. Language is the thread that ties every other human advantage together. And for years, science thought it had found the single gene that switched it on. The story of that gene is the perfect ending to this list because it is both true and a warning. The gene is called FOXP2. It came to fame because of a single family in Britain, known in the research as the KE family, many of whose members struggled badly with speech, with the fine motor control of the mouth and tongue, and the grammar of language. The cause was traced to a mutation in this one gene.
Then researchers found that humans carry 2 tiny changes in FOXP2, not seen in other primates. And an influential study suggested these changes had swept through our species relatively recently, within the last 200,000 years. The conclusion seemed almost too neat. Here was the language gene, the molecular switch that separated talking humans from everything else. It became a textbook example, the gene that made us, us. And then it fell apart. First, when scientists sequenced Neanderthal DNA, they found that our extinct cousins carried the exact same 2 changes in FOXP2 that we do. That alone broke the story. Because if Neanderthals had the gene too, it could not be the recent, uniquely human spark of modern language. And it strongly implied that Neanderthals could speak as well. Then, in 2018, a major study reanalyzed FOXP2 across hundreds of genomes from around the world, and found no evidence of that recent, dramatic selective sweep at all. The original signal, it turned out, was largely an artifact of which populations had been sampled. The clean story of the single language gene, the molecular switch, simply dissolved. And this points at the deepest reason of all, the one that ties the whole list together. No other animal accumulates knowledge across generations the way we do. A young chimpanzee learns roughly what its mother knew. A young human inherits the pooled discoveries of everyone who came before. each generation adding to the pile rather than starting over. Scientists call it the ratchet effect, and language is the mechanism that makes it possible, letting hard-won knowledge, where the herds cross the river, which berry stops a heart, how a grandfather survived the winter of the great snow, outlive the people who learned it the hard way. A single human is fragile and forgetful. A culture, bound together by speech and carried forward through time, is something close to immortal. And it was that, far more than any one gene, that walked us through the Ice Age and out the other side. The collapse of the simple FOXP2 story did not leave us with less. It left us with something richer and more honest. The same gene, in slightly different forms, turns up in songbirds learning their tunes, and in bats navigating by sound, which tells you it is part of an ancient toolkit for controlling learned vocal behavior, not a bolt of lightning unique to us. And the evidence that Neanderthals could speak has only grown. Their throat anatomy, the tiny hyoid bone that anchors the tongue, and even the bones of their inner ear, which appear tuned to the same frequencies human speech uses, all point to cousins who could talk. The gulf we imagined between us and them, with language on one side and silence on the other, was never really there.
The body itself was rebuilt for talk in ways that go far beyond a single gene. Our voice box sits low in the throat, creating the long resonant chamber that gives human speech its range, a configuration most other mammals lack. We have astonishingly fine control over our breath, metering out air across long spoken phrases, and the evidence keeps pointing to our cousins sharing the foundations of this. The Neanderthal hyoid bone, which anchors the tongue, looks essentially modern, and influential researchers have argued that language is far older than our own species, already present in the common ancestor we share with the Neanderthals. The story was never about a switch flipping on in us alone. It was about a slow, shared deepening of a power our whole lineage was growing into. It is worth remembering, too, that the Neanderthals who shared this gene were no brutes. They buried their dead, used pigment, made ornaments and tools of real sophistication, and cared for their injured.
Everything we learn pushes them closer to us, not further away, which is exactly why the collapse of the single gene story matters. What set our lineage apart was never one lucky mutation that they lacked. It was something subtler and more powerful. Larger, more connected populations, trading ideas across great distances, accumulating and preserving knowledge until the pile grew taller than any one mind could ever build alone. The advantage was never in the gene. It was in the network. So here is the real ending, and it is bigger than any one gene. FOX2 is genuinely important. Break it, and speech breaks, which is why that British family struggled. But it is not a magic switch, and it is not ours alone. There is no single gene that made us talk. Language emerged from the slow interplay of many genes, a reshaped vocal tract, a rewired brain, and, above all, a culture that gave those tools something to do. The thing that truly separated us from every other predator of the Ice Age was never one mutation. It was the ability to pool our minds, to take everything the shoulder and the sweat glands and the big, expensive brain made possible, and to bind it together with shared words, shared plans, and shared memory that outlived the people who made it. Other animals had their bodies. We had each other's knowledge. That is the reason you are here. Finale. So line them up, the 10 reasons you are alive. A catapult in your shoulder, 4 million cooling glands in your skin, eyes built to be red, a nose that tames frozen air, an ancient famine gene, a sleep compressed and staggered against the dark, 2 gifts of DNA from a vanished species, the most expensive brain in the animal kingdom, and the shared language that ties it all together. Now look at what the mammoth had.
It had size and a coat and tusks and a body magnificently adapted to one world, the cold, open mammoth steppe. It was a specialist, perfected for a single way of living. And that, in the end, is the whole story of why you are here and the mammoth is not. When the Ice Age ended and the climate lurched into something new, when the steppe turned to forest and bog and the old world dissolved, the mammoth could not change fast enough. It had one strategy, and the strategy ran out. We had 10. We could throw, run, read each other, breathe the cold, gorge and fast, sleep in shifts, borrow solutions from other species, plan and talk. And when none of that was enough, we could invent something new within a single lifetime and teach it to our children. The mammoth met a changing world with a fixed body. We met it with a toolkit we could rewrite on the fly. And in many of the places where these two stories crossed, it was us, with our spears and our plans and our shared knowledge, who helped write the mammoth's last chapter. The mammoth's end was not simple. The debate over what killed the great Ice Age beasts, a warming, lurching climate, or the spread of human hunters, has run for decades, and the truthful answer is almost certainly both, working together. A changing world shrank and broke apart the habitats the megafauna depended on, and into that stressed, dwindling world walked the most adaptable predator the planet had ever seen, armed with everything on this list. How large a hand we had in their end is genuinely debated. On continent after continent, waves of large animal extinctions line up unsettlingly well with the arrival of modern humans. In Australia, tens of thousands of years ago, in the Americas around the close of the Ice Age, a pattern stark enough that some researchers argue human hunting was the decisive blow. Others insist climate did most of the work. The likeliest truth is that the two together formed a trap with no exit. A warming, shifting world that battered the megafauna, and a clever, relentless, cooperative new predator that arrived to finish what the climate had started. There is one last detail that captures the whole tragedy. The very last mammoths did not die on the Great Steppe at all. A small population clung on, isolated on Wrangel Island off the coast of Siberia, and they survived there until roughly 4,000 years ago, which means the final mammoths were still alive. When the pyramids of Egypt already stood, the species did not fail all at once. It dwindled, stranded, outlasted by the very people who had once hunted it across a vanished world. Step back, and the contrast is the entire lesson. A mammoth was a masterpiece of specialization, a single magnificent answer to a single kind of world. We were the opposite. A jack of all trades, master of none, with a body and a mind that could be repointed at almost any problem, and a culture that let us keep the solutions. Specialists win, gloriously, right up until the question changes. Generalists endure, because they can change the answer. You did not survive the Ice Age because you were the strongest thing in it. You survived because you were the most adaptable, the most cooperative, and the most relentless. And because you carried the accumulated solutions of everyone who came before you. All 10 of those reasons are still inside you right now, in a body that was forged in a frozen world that no longer exists. The Ice Age is over. The animal it built is still here, reading these very words. If this changed the way you see your own body, subscribe, because there are far more of these buried stories to tell. And tell me in the comments, which of these 10 surprised you the most? Until next time.